Julie, you're back online?
Yes, I'm here.
My computer. You know how to use the pointer, guys? Here. So this one is here, and this is your third button here. You can do laser pointer.
Cool. Is there a way, I wonder if we could swap which screen is the display and which is the presenter view? I think there might be a hotkey at the top. Yeah.
Oh, your comments are visible, so you guys are like, okay. You want to keep it hidden, right?
Don't worry, nothing too bad in there.
This
That's
thing you
it,
can
see.
play with it.
Oh, how do I get off of this laser pointer? Uh, just give me an arrow. So I want, yeah, I don't know. I just want to switch these around. How do I get this red dot back to a regular pointer? Oh, never mind. Found it. Yeah. Which, I can't see them. Which one is, what are those? Awesome. That's what I want. Great. Now I think we're ready to rumble.
So Julie, can you see the presentation?
Yes, I can.
Shall we? Do it. All right, thank you, everybody. As we got everything sorted out, John and I are going to talk about precipitates. So I'm going to focus more on imaging after a brief introduction, and then John will transition more into diffraction techniques. I think starting off, one thing I just want to lead with is that there's really no one-off technique that is perfect. Really, it's using complementary techniques to get the information you need that is the most critical aspect of these. So first of all, what is a precipitate? So in precipitate, especially my background's in metal alloys, so I'm kind of speaking from there. Precipitates are dispersions of second phase particles within the original matrix. So generally speaking, they're in metals, especially precipitates are often intermetallic compounds. They're often created during a heat treatment of a metal as solute atoms come out of solution and form distinct second phases. We care about them because they precipitates provide strength and other properties benefits. They act as obstacles for dislocations. In the nuclear zone, which we care about a lot, they act as traps and recombination sites for defects, which is critical to controlling microstructural evolution during irradiation. That trapping occurs at interfaces, the interface between the precipitate and the matrix it rests within. So you see, once I turn this laser pointer back on, see in the bottom left here, these interfaces can have a couple of different types of qualities. So you can have a coherent interface where the precipitate lattice planes link up with the matrix lattice planes, although if there's some lattice difference, as shown here, you have some corresponding strain that goes along with that. You can have an incoherent, fully incoherent precipitate where there's no match at all between the lattice planes. And then finally, a partially coherent precipitate where you have occasional dislocations introduced along the interface to relieve some of that lattice parameter mismatch strain. On the right here is just a TEM bright field image of this is an aluminum alloy with some precipitates. So you can see there's both a kind of dispersion of them within the grains, as well as they tend to also congregate at grain boundaries, often, although not always, in even greater amounts. And I will say, so carbides are a very important type of second phase that are present in almost all metal alloys that are similar in some ways to precipitates, but distinct in others. I think generally they generally have higher melting points and form earlier in the processing process. I would say also they tend to more heavily favor appearing on grain boundaries as opposed to within grains. But a lot of the techniques that we're going to discuss are also applicable to carbides in the sense that there are second phases that you want to get information about, and they often have similar properties impacts or can have overlapping properties impacts with intermetallic precipitates. So just a quick overview here. So John and I think we both agree that this project has really just illuminated to us how much there is that we don't know about in the field of TM with regards to precipitate characterizations. You can see here in this graphic, this kind of broken off, starting from the inside, working out. You can think about different techniques, primarily belonging to imaging techniques, fraction techniques, or spectroscopy techniques. And then there's some also specialized in situ TM and tomography for three-dimensional reconstruction that we're not going to focus on as much today. But imaging, so you have then the dominant techniques of bright field, dark field, high resolution TEM, and high angle annular dark field, which we'll talk about in turn. And then on the diffraction side, you have a variety of techniques as well. And so each of these can be used to unveil different properties about the precipitate. So what do we care about? Oftentimes, especially for nuclear materials, because we're concerned about precipitates as defect sinks, we want to know number density. So we need to know, their spatial relationship to each other and the frequency they appear with in the sample, the shape, and the size. So these various techniques can be used to acquire these properties as shown in this table here, and sometimes in combination. So there's not really, for example, for precipitate number density, there's not a one-shot technique that you can immediately apply and get it, but you have to combine, say, using high angular dark field to kind of do a precipitate count, and then perhaps eels to determine the thickness of your specimen, and from there calculate the number density. Composition and crystal structure are, of course, very important as well. Crystal structure being more most easily determined with diffraction techniques, and composition, I think most commonly, X-ray spectroscopy seems to be the most commonly used, but eels, I think, can also be used in that respect as well. So I'm just going to press on here. Before we get into the specific types of imaging, I just want to talk about contrast very briefly here. So in the top right, there's the schematic indicates what do we mean when we talk about contrast and intensity. So intensity is the in the wave sense, you think about it as like brightness or flux, and in the particle sense, current. So it basically is like how much signal are you getting? And contrast then is the difference in that between two different areas. And as shown schematically here, generally speaking, if you at lower intensity, you tend to have better contrast. And conversely, with a higher overall intensity, you tend to have a little bit less contrast. And this will show up in some of the imaging techniques that we'll show with bright field tends to have higher overall intensity because you're taking a direct beam without selecting any diffraction spots, but dark field tends to have a better contrast because you're filtering out so much that background when you go to select the Bragg beam in particular. So contrast itself can be broken into different types. So maybe the most simplest is just mass density contrast. Electrons are deflected more when there is more mass present. So you can see in this image, these are just some latex particles on carbon. This is from Williams and Carter. Many of you probably recognize it. But these thick spheres prevent a lot. They're much. There's a lot more mass to scatter through than the thin carbon film around it. And that contrast is shown there. Another type of contrast is diffraction contrast. So by tilting your sample, you can enhance Bragg diffraction from select regions. So on the bottom left here, we've got these cubic nanoparticles in iron, and you can see some of them are more or less contrasted with the background. And this is because each of these cubes has different orientations, and depending on the specific tilt angle here, some of them are diffracting more than others. Then finally, and I think John will touch on this a little more later, phase contrast has to do not with the material phases, very confusing. But the electrical phase difference between two out of phase electron beams, that is in the two beam condition, rather than say just moving your aperture to only select one Bragg beam, you allow two beams to interact with the sample and then pass through to be imaged, kind of as shown as this energy filtered image on the bottom right here, which you, as John will explain later, you need to do a little more legwork to deconvolute what you get from that, but that can provide you information that you wouldn't get otherwise.
Shradha has it.
Please do.
Intuitively, when you look for the state, when you look at the diffraction pattern, coherent, your lattice are oriented. They have slight relationship to them in terms of your diffraction pattern. In other case, you would not have incoherence. So what kind of what do you think? Making more difficult as progressing with this class now.
Sure, yeah, just to expand on that, like the concept of an orientation relationship is present in many systems that have these second phases where if I identify a zone axis or a crystallographic axis in the matrix phase, there are often rules that are followed by the precipitates or second phases, such that in perhaps relative to the 100 plane in the matrix phase, that may directly kind of build into the 110 habit plane, I guess, of the precipitate. And so based on that relationship, then when you're, say, looking at a diffraction pattern, you can start to identify which spots correspond to which things. Is that what you were getting at, kind of, or?
So much coherent. The zone axis of both, which is very rare in general. In general, you see an orientation relationship, and if you see a clear orientation relationship, you will see the diffraction pattern overlapping. So this is the number one point, which is of top importance, especially to the research here. There are research going on both actively in Brian's group and Winkle's group to just examine coherent precipitate either theoretically or practically in variety of nuclear materials. Any nuclear materials that we think we can put, this is first thing we test. Now, going back to the second slide, the important information is this little table he put it. This should be in your mind all the time. For the orientation, you will do simply bright field, dark field. That means just selecting the points in the diffraction pattern. Now, size distribution, we are learning something new today about Haddon. And these ones are very important to you, the yields. Yields is something that tells you about the chemical composition, whether it has silicon, iron, chromium, what in your precipitate. So overall, you can just separate into three main techniques. One is your bright field, dark field. Other is your Haddon and yields. So anyone who can do these three can do a lot.
One thing I'd like to add, one of the most, we haven't covered it yet, but okay. One of the most powerful techniques for determining the orientation of precipitates is actually doing lattice imaging with high resolution TEM. That's arguably the best way to study the orientation relationship between your matrix and your precipitate phase.
The third slide. This is again a very good summary. I also have in my lecture. The one thing he told that you have to do high resolution imaging to know the orientation effect. What is the contrast you think among the three you would use?
We're going to talk about that later. That's phase contrast.
Yeah. these are the three contrasts that you would talk about consistently. And here the contrast is occurring because there are mass difference between the two things. Then there is a diffraction contrast because there's a different scattering happening because of different precipitate and the matrix. And then the phase contrast is, we'll talk about it. It's one of the most important things. Yeah, go ahead.
One thing, just to go back to this real quickly, I would say for many of these, properties that you seek to get, you could use a variety of different techniques to do so. This table is more or less just from what I've seen in the papers that I've read, what's most common.
So like first primary techniques to begin your experiment with.
We'll add too that, so our presentation is more or less focused on precipitates, imaging, and diffraction as a whole. Really, so after our meeting, kind of breaking into the imaging that all the specific techniques you can get into with the interface, with imaging, that relationship, and the strain fields and so forth around that is like that could be a whole presentation on its own. So in the interest of brevity, I haven't added much on that, but I'm thinking when I present for Dr. Zinkel's group, that would be some good additions I could make in the interim. So just to bear in mind, there's even more there than we have in here, but I guess if you're a Zinkel group member, be on the lookout for that in the future. Okay, so bright field, yeah, this is I think regarded as just kind of the simplest or most intuitive. So as you can see here, you're selecting the direct beam on the optic axis as it passes through your sample, and it's just a relatively straightforward and intuitive image. So as said here, thicker or higher mass areas appear darker. And one thing I wanted to note is that this is always to keep in mind with these imaging techniques, but this is a 2D projection of 3D space. So I wanted to include this figure from Williams and Carter, just that unless you know specific things about your sample going in, you can't always assume that, oh, I see a circle, it must be a sphere. So in this case, they sputtered some carbon on at a very oblique angle. And based on that, in that case, that told them, okay, these are in fact spherical. Now these aren't necessarily precipitates, but just as a useful imaging thing to keep in mind, I wanted to include that. Also, I did read some paper. So there are certain cases where precipitates or microstructural features were observed in bright field, but their diffraction spots were not seen, whether because they were early in the nucleation process or just a very low volume fraction. So while bright field may be perceived as like a kind of somewhat simple or elementary imaging technique, you can catch things with that if you're looking closely that you may miss with some of the other things. And then just an example here. So as I mentioned earlier, bright field having higher intensity also tends to have a slightly worse contrast. So in the top left here, this is an Inconel 718. So a nickel superalloy, pretty heavily alloyed. We've got a nickel matrix and then intermetallic precipitates referred to as gamma, because the matrix phase is referred to as gamma. So here on the top left here is a bright field image showing you've got various types of phases going on. Maybe some thickness variation in the lamella itself. It's hard to look just at this bright field image and say what's going on with this microstructure. So we'll get into diffraction more later, but these are 3 selected area diffraction patterns taken. These are all taken at this spot A of gamma here, but along different zone axes. And you can see these kind of superlattice spots that are arising from the presence of the gamma prime precipitates have different orientations relevant to the main matrix spots, depending on the orientation that you rotate through or what your zone axis is that you're using. This is just to highlight that, bright field is useful and can help give you kind of an overview of what's happening, but is on its own, you need other things to kind of break that apart into its constituent components. Do you have something, Shradha? Yeah, please.
take it to another zone axis. Just, I come here, then I just move to a Kikuchi line and I go to another zone axis. Would I be seeing do you think that I would be seeing this or this relationship?
The answer is not necessarily. This all gets into the coherence of your precipitate and how it's sitting within your matrix structure. Because sure, you might see this relationship at this angle in the zone axis, but depending on the crystal symmetry of your precipitate, depending on its orientation, if you just go to another zone axis, there's actually no reason it should look the exact same. Yeah.
An important point that he mentioned, why bright field image can be an important technique. It looks to you when you do it, oh, it's the basic thing that you do. These spots here, sometimes they are not very clear, the particular zone axis. And you tend to miss the precipitate because the volume is so less, because they're underdeveloped. So you would see them as, merely one spot here, and then you would be totally confused. Are these spots coming from, precipitates? And if you do a thorough analysis, you would see, yes, there are present these little spots. So as a primary investigation, bright field is the #1 tool. Another important point that is there in one of the slides, can you go back? I emphasized one thing. Remember, I gave a big lecture on sample preparation other than FID. And this sample preparation, whosoever will do precipitate analysis in their career, they will use something known as carbon film deposition. I talked about it. I told that there are samples which has precipitates into it. We take that sample, we put them into a little instrument from where the carbon is deposited on the surface. And then we take that sample, and we try to etch the carbon. Carbon layer, it tries to become like a little, now it is separated from the sample. And that contains precipitates. It's a very common technique. And people who will be working with ferritic martensitic steel, your pressure vessel steel, which is like majority of us, they work, especially from Steve's group, they would be using this technique. So this was your sample, beautiful sample that you created these precipitates. You deposited a carbon film, then like a tracing paper, you take that carbon film out through a etching. And this is what you're seeing. It's a technique that takes little mastery, but it's very common. So for precipitate, other than FID, this technique, right? Yeah, so there are some chemicals like that they won't do anything to the carbon film and to the precipitate, but they would be able to separate it.
So that's what you're talking about, or are you talking about you're etching away carbon?
I'm not etching away the actual carbon. I'm trying to just separate the carbon layer with the material.
That's what the precipitate is.
Yeah, it's just like I take a carbon paper, I put it here, and then just try to separate. So depending upon the composition, we have to play with the chemical, but very, very well known. Yeah.
On the dark field, so Thomas in the presentation spoke about, and as we see in the video, basically the idea is you, in dark field imaging, rather than taking the direct beam, you take a refracted beam, which then gives you information relative to the plane to the beam that you select. So, off-axis dark field, you just move the aperture, you select the Bragg beam that you would like, whereas in center dark field, shown here, you adjust the optics such that the diffracted beam you want is centered in the optic axis. So conversely to bright field, in dark field, thicker or higher mass areas appear lighter. Let's see. As I said, desired diffracted beam must be chosen and the aperture adjusted to let it pass through. And it tends to have lower intensity than bright field overall, but correspondingly tends to have higher contrast because you're only getting the signal from the diffracting features, and so much else is just being blocked by the aperture. This can be helpful to let small features pop out more as you have these, basically the white signal on a black background that's very visually apparent. And just to emphasize, each diffracted spot corresponds to a specific set of HKL planes. So again, if you know the orientation relationship that you're looking for, that can point you in the direction you want to go to. So just an example of this, here's a centered dark field example. This is a commercial nickel alloy Haynes 244. This is a heavily alloyed nickel alloy FCC matrix, and it has Perhombic precipitates of the nickel 2 moly stoichiometry. And you can see here, depending on the zone axis you're looking down, as you see by the selected area diffraction patterns in the insets here, 110, 010, you can get very different information about the same precipitate network that you're looking at. These precipitates are, they're lenticular, so kind of lath shaped. They're very long on one axis. On the left side, you're basically looking normal to the habit plane. And on the right side, you're looking parallel to the habit plane. So you can see here, you get a very different, if you were honestly not unlike the G dot beam analysis in with the 2-beam condition, you have to be very conscious of what you're counting in a precipitate distribution, and what measurements you're taking could vary depending on the perspective you have looking at it. So for in this alloy system, for example, there are 6 directional variants of these precipitates with respect to the matrix. So to image them all, they had to walk through I think 3 different combinations of zone axes to be able to capture them in every orientation they're looking for. Do you have anything, Shradha, or should I press on?
Sit on the microscope with me, I tell you to do that. You do. I feel this part, just move this part, select the G part, into the dark field. So simple that the objective lens, just select the G part. Now in the center dark field, you know one thing, that you can translate your electron beam, right? So in the center dark field, you are bringing your G spot in the center of the beam. And any comments? How would it change your analysis? Go ahead with you. This is a question. I would touch the base again. Center dark field, normal dark field, which is used in which scenario? Why should I move from my dark field to center dark field? What in which scenario?
I think I will have to add that for the Dr. Zingle presentation because
Good question.
I do not have a good answer.
I have a question there. The TA part before starting the machine. All these points, because these are your tools.
Okay, so moving on from center dark field is a variant high angle annular dark field. Oh, okay. Okay, so as opposed to basically for techniques we already discussed, the beam passes through, and whether it is off axis or centered, you ended up just going straight down the optic axis to the detector. High angle annular dark field in this case is makes use of an annular or ring shaped detector. So if you have your optic axis going down here, or if I'm the optic axis, then your detector is like in a ring around the optic axis. What does that capture? That captures electrons that are scattered at high angles relative to the optic axis. So what does that mean? So first of all, high angle is anything greater than 50 milliradians. And then there's also annular dark field, as distinguished from high angle annular dark field, that is from 10 to 50 milliradians. We'll start with high angle annular dark field and then work back. So with high angle annular dark field, as electrons are traversing your sample, you have Rutherford scattering of those electrons, which means that you have a heavily Coulombic scattering event happening that can deflect electrons to very high angles. And the severity of that scattering cross-section scales almost according to z squared, based on the, being a Coulombic interaction. As you have more charge, you scatter more strongly, which means that high angle annular dark field gives a very good z contrast, enabling you to distinguish between unlike elements pretty well. So this is often, for this reason, because you get this, very precise, distinction between different elements. This is often used for the size and distribution measuring of precipitates, because you can distinguish between the precipitate and the matrix most easily. Another advantage of high angle annular dark field is because you're collecting signal from this annular region around the optic axis, your direct beam is still passing through, and that can be passed through to other complementary simultaneous techniques, such as most commonly EDX to collect compositional information, which we'll get to a little later, or something like EELS as well. Annular dark, so just to come to the slide here, this schematic in the middle kind of shows, here's your beam coming down. You've got, for example, a bright field detector centered on the optic axis, slightly outside of that, at the furthest extreme, highest angles, you've got your high angle annular dark field detector going around here at this higher angle. And then in the middle, you have another detector. You can have other detectors, the annular dark field detector, which that is similar to high angle annular dark field, but scattering at this angles, you can start to pick up things like strain fields. For example, here this is an image on the left and right. The insets here show the angle. So on the left is HOTF with this 50 millirad high angle, and on the right is angular dark field at 25 millirad. And so it's the same interface. You can see this with high angle annular, it looks very just cut and dry. Here's one phase, here's another. On the other image, the angular dark field, you can start to see the at this interface, you can see these first few planes are showing. Well, one point to make about this is that you don't know, just based on the image alone, what phenomenon is causing that difference in contrast. In their case with the sample, they know that there's probably some strain present here, so that's how they interpret it. So this angular dark field, you need a little more contextual information to be able to interpret what's going on. But it can maybe reveal things that wouldn't be otherwise specified. And I think that's something, my second presentation, I'll end up expanding on more, because that's something especially with regard to, strain around an interface, it's a very important phenomenon for our purposes. I believe it is predominantly STEM, although I wouldn't bet my rent that it is never used in that case. Sure.
Talked about it, and we have another form, the electron beam, it interacts with the nucleus, right? Now, there are one thing we are getting. This interaction of electron beam is with electrons or nucleus for hand.
It is. So the nucleus is the main scattering center, but the core electrons around it can also screen that. So, I mean, I guess there's a contribution from both, but I would say the nucleus ultimately.
was very important. You had a, you're just trying to know if it's silicon, if it is oxygen, or if it's aluminum. And we are putting two detectors. One is a low angle angle detector, and one is a high angle, right? So what we are doing is electron is passing. It is just interacting with the nucleus. Some of them nucleus could be multiple nucleus. It can be a silicon nucleus, oxygen nucleus, or whatever is here in the material, right? Silicon, oxygen, nitrogen. I will go a little heavier. I won't go below oxygen generally. And then what happens is some of them it scatters here, and some of them it would scatter at a higher angle, right? And then this is telling me the entire. This is giving me the entire composition of your sample, right? Like this. So this is a header which tells you the composition of precipitates. STEM means STEM. Whenever you have this term scanning TEM, we talk about coming to the zone axis and doing the analysis. It's more of the term that we use that we don't go to G's. It's an overall technique. So STEM is scanning transmission electroscope microscopy, where you're literally scanning your transmission beam. So to have these images. So this is something very important. There are detectors ADF and HEDF, which just tells you which element is present in your material through any technique that you do, which can tell you the composition. Any question here? Any question here? Yeah.
How good is the composition, like resolution? Like, can you tell, like is it just kind of saying like these elements are present, or can you actually get like concentrations out of it?
That's why what Ryan said about pairing this with EDS detector, since you still have that directory, that's where it's really important, because HADF and angular field, they really just tell you that there is a compositional difference. You can infer information about the intensity. So a really high intensity point in your HADF image is going to indicate a heavier element, but it's not necessarily going to tell you what it is. And that's why it's really important to pair it with a compositional analysis technique like EDS.
Gotcha. Makes sense.
Questions, guys? No, it's easy.
I'm glad somebody thinks so.
He's doing very well.
I'm good.
I'm enjoying it.
I'm good.
I will just want to illustrate this. So I want to emphasize that the technique you select is highly dependent on, first of all, the features you're looking for, and second of all, the specific system you're working with. So in this paper, this paper ultimately was comparing various characterization techniques, including some transmission techniques in SEM, actually. But they were observing here that for TEM, they were, and this is steel with some inclusions of niobium and vanadium carbides, and they observed that in HADF imaging, their vanadium carbides, and not shown here, they performed some EDX analysis that revealed the composition of each of these particles. They observed that the vanadium carbide particles were invisible. They weren't showing up at all in the HADF image. And so to try and figure out what's going on there, they use the technique which I've seen in a good number of papers, which is to simulate like computationally an expected image based on your microscope configuration and your sample characteristics. And what they found was, if in the event that they had a carbide particle slightly protruding from the matrix film, matrix foil, and not passing all the way through it, just by running a lot of iterations through, they were able to find that a condition like this would result in that vanadium carbide not showing up in the same condition where niobium carbide would. So this is just to illustrate that, different techniques have something that may work brilliantly for, nickel alloy with some orthorhombic precipitates, maybe not at all suited to something like this. So, I can't speak as much to the computational side, but I did observe in reading papers for this presentation that that's a frequent technique employed, is to, if you have an image, you're not quite sure what the physical phenomena are that are causing it, you may try and simulate an image and then tweak physical parameters that may be at play in order to match it, which is what was done here.
So, here's addition of a point. Everything that we are doing here can be simulated on computer, right? We know electron energy, we know the samples it is, so we kind of predict how the Hadoop image would be. Similar also apply to other techniques. This is what he's showing a good example. If you are for the Brian's group, it's good for the Brian's group. These guys, I don't know. I don't think they're doing microscopy, microscopy, especially totally, this one is simply simulation image that anyone can do it for you. Anyone can do it for you who's knowing these conditions and trying these conditions and predict an image. Versus this is what you have. You can simply, compare it. And you can guess things. And you can guess things. This is one of such examples. So this is one of such examples. Yeah.
So we get into some of those transmission techniques. So I think everybody at this point should be pretty familiar with the concept of characteristic X-rays. So as you have your instant electrons coming down and dislodge four electrons from target nuclei, after which outer shell electrons fall down, emitting that characteristic X-ray, which a spectrometer can pick it up and discern what element it is. So in this paper, this is a nickel alloy looking at some gamma prime precipitates. In this case, they had some precipitation occurring at a grain boundary. So in the top left here, you have your hot-F image, which shows, this is like mostly on Z contrast, but you have just various shades of blocky stuff. But then you compare that with simultaneously collecting an EDX map, and it reveals a lot more. So you come in here and see the top right here is titanium, bottom left is carbon, and bottom right is chromium. And you can see the respective Z's listed here. Kind of pair that up with the hot image. You can see here, if you look at these, it almost looks like the carbon and the chromium tend to cluster around the same spots. It looks like we'll see where these arrows lined up, but not always. You can see this chromium-rich area that it has no corresponding carbon-rich area over here. Conversely, you can kind of start to see that, it looks like the areas that are enriched in chromium are totally depleted in titanium, and they kind of almost are like a mirror image of each other along this grain boundary. Whereas also you can see then in the bulk, the chromium is very diffuse, as it's a solid solution strengthening element. It's pretty evenly distributed, whereas the titanium you can see is a little more, it's more almost concentrated because you have gamma prime that forms these titanium-rich precipitates that are, this is relatively zoomed out here with that 500 millimeter scale bar, but you start to I'm just including this to illustrate that, combining these techniques, you kind of start to pick apart, like structurally, what's happening here. One thing to note that, so like with many X-ray techniques, this breaks down with very low Z elements, like depending on your system below, like boron or lithium, tends not get anything, or certainly can't trust
non-quantitative.
Yeah.
Yeah.
Why is that? I taught you in the last class.
There's simply not enough electrons. That's basically it.
So light. Nothing's happening.
I think it's the next one.
Yeah.
Very, very well.
So
We're only at halftime.
Go ahead, guys.
Everybody looks thrilled, very alert. That's good.
let's talk about diffraction. No, Ryan did a really excellent job illustrating why imaging techniques are really useful. They can tell you where things are located, to some extent how they're oriented with the matrix itself, and then as well through compositional techniques, they can tell you kind of what you're looking at. But one of the key complementary techniques to always use is diffraction, because that can really tell you exactly what you're looking at and how it's oriented. So the concept of diffraction is basically when you pass a beam through a gap where that gap is somewhat similar to your wavelength, you are going to experience a diffraction of that beam. In the case of crystal lattice, when you're working with something like an electron beam or an X-ray, that wavelength is close enough to the lattice parameter that you're going to diffract the wavelength itself. So this is dictated by something called the Bragg condition. On the right here, you have n lambda equals 2 d sine theta, where n is your order of order of reflection. Lambda is your wavelength, so that's either proportional to if you're using X-rays or electrons. It's also proportional to your beam voltage. On the right here, you have D. D is your interplanar spacing, so that's kind of like what gap you're talking about here. And then theta is the scattering angle of the beam. So on the right here, there's a figure showing how you can see when diffraction's occurring. The key thing here is that the Bragg condition doesn't necessarily dictate whether diffraction itself is occurring, because diffraction is going to occur when you pass something through that gap. But the Bragg condition tells you when you're going to get a diffraction that causes constructive interference, meaning that you're going to see a high intensity spot indicating that diffraction occurred. Whereas when you don't meet the Bragg condition, you end up on the right here, where your difference in path length results in a destructive interference, meaning you see absolutely nothing. So to talk a little bit about the difference between imaging configuration and diffraction configuration in a TEM. The thing to remember here is that both of these signals always exist. When you're passing an electron beam through a material, you're creating an image and you're also creating the diffraction image. It's all about how you set up the microscope to determine which of these you want to see. So in the microscope itself, you have different kinds of diffraction images. You have selective area diffraction. So that's when you have a parallel beam illumination of your sample. You also have convergent beam illumination, convergent beam electron diffraction, which a little bit self-explanatory, but it's when instead of a parallel beam illuminating your sample, you have a convergent beam coming into a point. So in order to switch between these modes on the microscope, all you really end up doing is swapping out an objective aperture and inserting a area diffraction aperture, as well as configuration of the projected lens to change what's actually getting sent to your image plane. So it doesn't take much, and that's what allows you to really rapidly switch between image and diffraction mode in a TEM. So to talk a bit about selective area diffraction. So selective area diffraction in the context of precipitates is kind of your bread and butter. It's what's used 95% of the time. Convergent beam electron diffraction has a lot of positive aspects to it. It can do some really powerful crystallography, but it simply just does not get used very much for precipitate analysis.
Question.
Yes.
This is for everyone. Pretty obvious, right? Should be very obvious, right? For example, you precipitate. Call it sometimes. I call it sometimes. The dirt. It's the dirt kind of a thing which is present on your clean matrix. Now you want information. From only this area, right? Only this area, right? Anything from here and here. To do that. So to do that, we are using constantly two terms. One is selected area, and other is conversion beam. Right? So why and selected area? So in selected area, I'm selecting only this area. From the sample I have just done something. Insert an iron plate with a hole. And everything is getting blocked. This is my sample only. I don't care about anything else. That's what it does. So the information is not taken out from outside. It just literally put a kind of a hole here. In conversion beam, what I am trying to do is I do not. So in the parallel illumination, your entire sample is getting illuminated. In conversion beam, I'm literally targeting my conversion beam here at a spot. Again, this should be a follow-up question. Conversion beam versus SAD. Which should I use and why?
Well, the first question is it depends what you're trying to find out. Okay. You can use seabed for really advanced characterization. You can also actually use seabed to determine your sample thickness. The problem with seabed is while you can get an extremely small spot size, like on the order of a couple nanometers, the intensity is extremely high. So if you have a really nanoscale precipitate and you're trying to do like nano or microbeam convergent diffraction, your background signal is going to be very substantial. So that's why a lot of the time selective area diffraction is actually used for precipitate analysis, just because you're working with a pretty small amount of material. So if you use a convergent beam, you're going to excite a lot of background information as well from the matrix. But the very small spot size from convergent beam is pretty important because selective area diffraction, it's kind of tough to really get a aperture below like 200-ish nanometers.
Any question on what he said? He just said everything, I think. Very well. So the clear difference between CVD and selected area, when you think in mind, in CVD, you are converging a beam. That means you're making your beam high intensity. So it is still coming from the entire sample. It carries the entire background. So you are not able to separate anything much, or you're getting a lot of background. In case of selected area, what is happening is he's just selecting this area. And he is trying to get information only from that. That's why most of the techniques they are using your SAD more than CVD. Yes.
A little bit like why you're getting more background at higher density, like intuitively I would expect to get like more signal.
I mean background. When I say background, I mean matrix. You're not getting like digital noise, you're getting matrix information. Like think when you take a magnifying glass, you're creating a super high intensity spot. So you're just putting a lot of electrons through that. So you're exciting a larger interaction volume. Yeah.
Like, I think too, what he's like, what else we think about it is like, so in this foil, you know, you may have a 50 nanometer thick foil, but if your precipitate is only 10 nanometers within that, you know, then 80% of that vertical cross section is matrix and not precipitate.
C versus CVD, not clear comparison. Till a point. SAD, we told, apertures, we don't have a bigger aperture for SAD. Like how much small you can think your iron plate could be that is just blocking everything. I mean, how small you could think. You cannot create the, very small nanometric sizes. It's still in micrometers. Right? So in that case, you are good. You choose SAD versus CVD. And you just choose SAD till a point. But after that, you need very small thing, you need to have CVD, right?
Or that's where you start to do fun stuff with high-res TEM. Lots of fun techniques. So I illustrated a cool example here. This is, so a big part of the work group is studying fission product transport. Instead of actually talking about purposefully making alloys, we talk a lot about how fission products get transported through stuff like your fuel, stuff like your cladding, and how those fission products might agglomerate in certain areas and form precipitates. So in this context here, you have a silicon carbide layer in a trisoparticle, and you have silver and palladium migrating out of the fuel kernel and migrating into the silicon carbide. So one question is, how are these fission products migrating in the silicon carbide? And in this case, it was found that palladium and uranium were actually forming a silicide in the silicon carbide. So they indexed this, they figured out the crystallography, but it raised one interesting point where, because the atomic radius of palladium and silver are literally the same thing at 0.144 nanometers, you can't tell the difference because it makes the same crystal structure. So SAD could tell you the crystal structure of what precipitate you were looking at here, but it couldn't tell you the exact composition of it. And that's why it's really important to use multiple techniques to kind of cross-validate everything you're learning with each technique. So here's a eels slide that actually Ryan's going to talk about, except it's in the wrong place.
No problem. It's just as good here as anywhere. So eels, electron energy loss microscopy. All that electrons can interact elastically with your sample, scattering objects, or they can operate inelastic, losing energy as they pass through. Eels exploits this in the sense that you can record with the direct beam, often in conjunction with collecting angularly scattered information. You can, knowing the incident energy of your electrons, which you can know pretty well, and with some corrections and things, and then it's seeing for how much energy they lose on the way through. You can collect these spectra shown on the right. So this is basically counts by electron energy, counts on the vertical axis by electron energy on the horizontal axis. So they're, based on there's some difference between your incident beam that is hitting the sample and what passes through and what's recorded by this. And I won't get totally into, EELS is very complex. You can break that signal into a lot of different information. Some of it's like electronic structure and that sort of thing. You can get some compositional information, although I think EDX is generally more used for that just because it's easier. It primarily used for the average user, I would say, at least in my perception, is to determine thickness, the precise thickness of your lamella within about 10% or so, based on the papers that I've seen, at specific points. You can see on here, it's kind of a little hard to see on the screen, but there's 5 red numbers indicated on that lamella, 1, 2, 3, 4, 5. Spots 1, 2, and 4 correspond to these plots here. So you can see that they've taken these spectra, they've done the number crunching necessary, and they've come up with, okay, spot 1, 72 nanometers thick, 2, 80 nanometers thick, 4, 111 nanometers thick. You can see even with very precise polishing, you know, that's a, what, you know, 30% variation from the thinnest to the thickest section. And if you're trying to use TEM to calculate something like precipitate number density, which is a key parameter for nuclear materials as far as sink strength, this you can introduce huge error if you're not carefully accounting for your sample thickness precisely in some way, whether it's by this or with CVED.
Yeah. So we touched on this a little bit earlier, but when you're working with any electron beam in a material, you introduce the concept of an interaction volume. So we talked about this a bit for seabed, but yeah, the interaction volume in a material is basically telling you for a given incident energy and for a given material, how big is kind of the sphere or teardrop that you're drawing information from, and where in that volume are you extracting what information. So let's say here, if you're interested in like the cathode luminescence properties of precipitate, but your precipitate's at the very top of that interaction volume, you're not actually going to get any of that interesting information if that's what you're interested in, because it's too deep in the interaction volume. So the concept of an interaction volume is one of the things that gives rise to like the superlattice formation that Brian touched on earlier, because you have, say, precipitate here and you have matrix here. You're exciting electron information from the entire thing. So you're going to have the primary diffraction pattern and the secondary diffraction pattern. And this is all because the sample's electron transparent and you have that interaction volume. So this also introduces a cool concept of when you have nanoscale precipitates, you introduce interesting kind of sample geometry problems. So when you have a matrix with like large grains, it's pretty easy to tilt and align to the zone axes you want without losing your sample. When you have a really, really tiny sample and you're trying to work with your alpha and beta tilts to orient to the right zone axis, if you have like a 5 nanometer precipitate and you're tilting through it, you're probably going to lose it. So that's why, sure, it would be ideal if you could orient to the exact zone axis you want in a precipitate, but if it's too small, you're just going to lose it. So it's an interesting point to note when you're doing sample preparation and TEM operation. The other thing here, which is the concept of what do the different intensities mean in a diffraction image? What does it mean when one dot's really bright and one dot's really small? So when you're working with something like X-ray diffraction, X-rays don't interact with charged particle with your periodic potential of a lattice. So what you really get is just the like theoretical crystallographic interaction based on your structure factor. So the intensity of a point with like X-ray diffraction, that intensity is just directly proportional to the square of your structure factor. But when you're working with electrons, you introduce the concept of like that electronic interaction between electron beam and electron cloud. And instead, your point intensity is actually starting to become proportional to the amount of multiple reflections occurring in your lattice. Because if you think about it, after you diffract the first time, you have a beam still going. That beam is still moving in your lattice, and there's still more planes for it to diffract off again. So if you have a thick enough sample, you're going to just have a whole bunch of multiple diffractions. And that is the concept of dynamical scattering, which is how electrons scatter in a material. So when you're looking at an electron diffraction image, that point intensity, it's no longer proportional to like your actual crystallography. It's just proportional to really how many multiple scatterings are occurring. So there are cool ways to minimize this. I've included a video that might play.
And with that, that is one of the key differences between extraction, COP, and dynamic versus kinematic. What are, tell me, how can I convert a dynamic diffraction to kinematics TEM? In dynamic, what he told was that what happens is in dynamic that we consider that we have multiple scatterings happening. Whereas in kinematic, we only have one scattering happening. So these all are examples of your dynamic scatterings, because that is why you have a different intensity. Now you convert into kinematic. That means I am talking about one diffraction point now. So this thing should be like sort of clear, and I will touch the base again. And I will give you a roadmap after everything, that what are the key points you need to keep in mind while doing your TM. So here, when you talk about your dynamic, you have multiple scatterings happening. And each one is, just take it as, different points that are you're doing. And in kinematic, you only have one point that is coming. So if I only select one G out of, all the Gs, I simply come from the condition of dynamic to kinematic, right? Because I'm just talking about one here, one spot here. That means I only consider diffraction in one point, right?
Is that talking about like the two beam condition? Yeah. So I've included a cool video here. There's a technique you can do. It's kind of covering the concept of the two beam condition, except instead of exclusively looking at one two beam condition, you pass the electron beam through the sample at an angle and you rotate the entire thing about the sample, basically exciting like every high order reflection possible. So in this video here, you see how it started with that dynamic condition where everything was bright. Now, as it's passing through a bunch of angles, integrating all of those different angles, you start to see the kinematic structure of your crystal start to evolve. So here you can see how it's gone from that dynamic condition to a lot of like discrete points where now your intensity is actually starting to become proportional to your square of your structure factor. So this is one way you can operate a TEM to have somewhat kinematic scattering occurring. And this is really useful for crystallographic determination of really, really small structures, or when you have basically no idea what you're looking at and you're trying to replicate the kinematic structure. Exactly, yeah. It's taking like the average every point. No, it's from a paper talking about deconvolution techniques. So Brian touched on the concept of phase contrast. Basically, when you pass a electron beam through a material, you're going to change, like if you're modeling the electron beam as an actual wave structure instead of like a particle structure, when you pass it through an electron cloud, you're going to alter the electronic phase, like the wave phase of your beam. So normally, the reason you use an objective aperture and a diffraction aperture is to isolate for which beam you actually want to look at on your sample plane. But if you pull all of the apertures out, now you have the diffracted and the transmitted image falling on your image plane, and you get a really funny image like you do on the bottom there. But there's a lot of really useful image in that uncorrected phase contrast image. So when you want to do the highest possible resolution TEM, called HRTEM or STEM, you're able to do actual lattice imaging, where now you're assessing how is the periodic potential of your crystal lattice interacting with your electron beam. And that's how you can do lattice imaging like that and actually do like 2 nanometer or like angstrom scale imaging. So the way you do it is you take this really deep fried image on the left here, and you do a lot of computation processing where based on your sample thickness, which you use eels to determine, your information about your crystallography, so your diffraction techniques, a general idea about your defocus distance, and then spherical aberration correction in TEM, you can do computational correcting to take it from this interesting left image to your actual right lattice image. And when you're talking about precipitates, this is extremely useful because now when you're trying to characterize like the orientation of a precipitate within a matrix, especially on the nanoscale, this is probably the best way to do it because you can actually view the different two-dimensional crystal lattices and how the different angles orient. So I've included an example here of a nickel-based superalloy with delta and eta phases. And you can see in the top, okay, in the top two images, you have really, really high resolution. So 5 nanometers and 2 nanometer resolutions with your different phases. And this is how you're seeing like the different orientations of precipitates within your lattice. On the bottom here is a really cool technique you can do to actually isolate the diffraction image from your high-res TEM image. By taking a fast Fourier transform, you can create simulated diffraction images of your two phases without having to deal with that superlattice phenomenon. And the key final thing to remember here is that high-res TEM is a 2-dimensional projection of 3-dimensional structures. So it's not perfect, but you can do further computational techniques to actually simulate and generate views of how your precipitate is sitting within your lattice at a 3-dimensional structure. So high-res TEM, it's a really useful technique, but it's one of the most complicated techniques you can do in TEM. I think.
Final slide.
Yeah.
Just going back
4:30.
around, showing, so this is actual neutron radiated in reactor stainless steel with some radiation induced precipitation here. I forget if it's on the boundary or just free floating, but you can see, so we've got a combination. You've got hot F image, bright field and dark field. So you can see, as you'd expect, bright field and dark field are very much complete inverse of each other. Hot F, you've got this, dark area kind of in the box area, which you can see with the UDX maps that seems to evidently be a manganese sulfide particle. So you've got, especially with the heavy sulfur concentration, it's a lower Z than many of the surrounding transition metals. And then you can see with some of the other things, you've got some silicon segregation that may be a nickel silicide. As you can see here, some of these points, nickel 3 silicon, precipitate forming these systems that may be forming there. Yeah, so I just, this was just a really nice paper, and I like the colors they chose for the EDX maps. So wanted to end on this. The key takeaway is that you can't use one technique for precipitate characterization. You kind of have to throw 4 or 5 different things at it, depending what you're trying to figure out. So it's really important to understand most of the different operational modes of a TEM if you want to do powerful precipitate characterization work. Well, that, I believe, concludes our presentation. So opening up for questions from Shradha or anybody else.
I will back on time on high resolution TEM and kinematic dynamics. Those are very important. And I did touch the base right now.
You can't really do it in 30 seconds. No. Yeah.
That has happened. Different terms, and this presentation, it makes you very handy that this is what you're doing rather than, I give you a bulk of, slides and tell you to do it. So these are very handy how the different examples and all these discussions, both is also there for your recordings. So, this is important. Like the Thomas, we discussed at the point that why we do 2D versus this thing here. There were important points of between CPD and SAE and had a low angle and high angle. Maybe we should have somewhere it is documented for you guys. And someone has to take the initiative because I don't have a TA. Somebody has to, have a videos are the best generally because you keep it. If you have that whatever. I'm looking for final takeaways from each project. Some key takeaways, and so they're like shorts. These days there are also like shorts, video shorts. You get YouTube becoming a huge business. There are some shorts after the project. I do shorts with them. So you guys on your that I created a little thing. That's why you're learning, especially for you guys, if you're doing the I heard about CBD versus I think I heard about it. How some of you apply. Love to have those interactive. Feel good. Touch the base.